Enzyme inhibition is one of the most common drug mechanisms and can essentially be defined as blockers of a specific biochemical reaction. This basic inhibition definition is reinforced by how they are usually described, with very simple inhibitor binding curves, allowing their inhibitory potential to be quantified with IC50 values. As was discussed in our previous video on binding curves, this simplified way of characterizing enzyme inhibitors is also ideal for the high-throughput screening processes used in modern drug discovery. But beyond this overly simplified description of enzyme inhibition, inhibitors are known to primarily affect two properties of enzyme activity. One, the rate at which the enzyme can convert substrate to product. And two, the rate at which the enzyme and substrate come together. Naturally, these inhibitory effects were classified as two distinct inhibition types: non-competitive inhibition, affecting the enzyme's activity, and competitive inhibition, used to describe inhibition affecting the substrate's binding affinity. Concepts that underpin our understanding of drug interactions but are in the end flawed. Competitive inhibition is believed to be caused by substrate mimicry, where the inhibitor competes with the substrate for the enzyme's active site. On the other hand, non-competitive inhibition, affecting the enzymatic reaction rate, may result from changes in the enzyme shape, effectively shutting the enzyme off, or in a mechanism similar to competitive inhibition. A non-competitive inhibitor might overlap the active site, preventing substrate binding. Both inhibition types rely on what is known as mass action binding, essentially equating increases in inhibition to increase inhibitor concentration, quite comparable to IC50 values obtained with simple inhibition curves. But what if I told you there's a problem with these ideas? Not the concept of inhibitor interactions, but the equations that were derived to explain inhibition. In fact, would you be surprised that, since it was proposed, around a century ago, inhibition that fits the competitive inhibition equation has never been observed experimentally? But how could that be? What are the criteria for the competitive inhibition equation that are so hard to meet? The competitive inhibition equation suggests that as the inhibitor concentration increases, binding between the enzyme and substrate decreases, as you might expect when an inhibitor blocks this interaction. However, the competitive equation suggests this interaction does not block the activity of the enzyme, but rather it is hypothesized to decrease the affinity between the enzyme and its substrate. This decrease in substrate affinity, according to the equation, is observable as a linear increase in the substrate affinity constant toward infinity, meaning the affinity of substrate for the enzyme continuously decreases with increasing inhibitor concentration in a linear manner. This linear change has never been observed. The main problems with the competitive inhibition equation likely stem from its initial derivation. While derivation of equations based on scientific observations can be a powerful tool for understanding how systems work, the derivation of the competitive inhibition equation was done during a time where complex analysis was challenging and in the absence of a lot of supporting data. But the methods used to derive competitive inhibition directly related to the methods that had successfully defined how enzymes interacted with their substrate, so they seem to have been accepted as theoretically sound. This was a big mistake. The continued failure to find experimental confirmation of the competitive inhibition equation was not taken as a falsification of the theory, but as the inadequacy of this relatively simple model to describe the complexity of the biological systems being studied. As such, a century of derivation later, the field has been blanketed in ever-increasingly complex theoretical equations, almost a new equation for every situation encountered. But all of them have been derived using the same base chemical principles, incorporating the same inhibition terms found in the most basic inhibition models, competitive and non-competitive inhibition. This has also resulted in the continued use and acceptance of the competitive equation in research and therapeutic regulation worldwide. But first, before we move on to the problem with the competitive equation, I think an easy way to conceptualize the interactions between an enzyme, its substrate, and an inhibitor is to think about a cat and its favorite sleeping spot. In this analogy, think of the cat bed as the enzyme and the cat as its substrate. The cat enjoys hanging out in its bed and after a while will fall asleep. As an enzyme changes substrate into product, in this case we can say the cat likes to sleep in its bed, converting the awake cat to a sleeping cat. Based on how much cats like to nap, we can say that if we place the cat in a room with a bed and come by occasionally, we will likely see the cat hanging out in or around the bed and may even see the cat sleeping in the bed. The cat's preference for the bed can be considered its affinity for the bed, known as the substrate affinity in the study of enzymes. Inhibitors in this example would be things that prevent the cat from napping in its bed. If we wanted to decrease the chances of the cat sleeping in the bed, we could do it several ways. One possibility would be to turn on a vacuum in the room. In this situation, the cat would still be able to hide in its bed if it liked, but would be too scared to sleep there. Another possibility is if we put a dog in the bed. In this situation, it doesn't matter how many times we drop by, we won't find the cat sleeping in the bed unless the dog decides to move. Both situations stop the cat from sleeping in its bed, representing a blockage of the enzyme's product formation, and would be expected to adhere to a similar model, which could be defined as, if there is something preventing the cat from falling asleep in its bed, you're not going to see the cat napping there. Alternatively, we could also reduce the chances of finding the cat sleeping in its bed by putting the dog next to the cat's bed. In this situation, the dog doesn't prevent the cat from getting in the bed or even sleeping there, but it does make the cat uncomfortable, decreasing how much the cat likes to nap there. This represents a decrease in substrate affinity for the enzyme and would likely result from an inhibitor changing the way the enzyme and substrate come together, but not actually preventing the enzyme from making its product. These two situations describe the simplest ways an inhibitor could interact with an enzyme and probably should have formed the basis of inhibition theory, but they didn't. Instead, the derived equations, while dividing the types of inhibition between a blockage and a change in substrate affinity, attributed any change in substrate affinity to a compound that mimics the substrate and blocks the active site. So, using our cat analogy, claimed that changes in how much the cat liked his bed could only result from the dog sitting in the bed, preventing the cat from getting in. But as implied before, preventing the substrate from getting to the enzyme's active site does not change its affinity for the enzyme, but instead represents a blockage of the activity. In reality, the most likely culprits for a decrease in substrate affinity, like a dog sitting by the cat's bed, should be attributed to crowding of the enzyme's substrate binding site or the induction of a conformational change in the enzyme, which, while not preventing enzyme and substrate from coming together, decreases the likelihood. This implies inhibitory interactions which affect substrate affinity should be represented as a system with two fixed substrate affinities, one for the enzyme and substrate alone, and one for the enzyme and substrate when the inhibitor is present. This simple shift in substrate binding between two states cannot rationally be explained with the competitive inhibition equation, because this equation requires a continual change in substrate affinity based on increasing inhibitor concentration. Truly, the only way one might be able to rationalize this sort of interaction is to assume that you could keep lining up as many dogs as you like around the cat's bed, with each additional dog increasing the cat's discomfort with the situation. But this doesn't conform with the inhibitor blocking the active site and destroys the idea that there is a specific interaction between the inhibitor and the enzyme. Now let's take a look at the classical equations for competitive and non-competitive inhibition. Both equations are expansions of the Michaelis-Menten equation, a simple mass-action equation used to describe the interaction of substrate and enzyme. Mass-action equations, also known as binding curves, are used universally for modeling molecular interactions and really just represent the percentage of something binding to a population of targets. If we use the cat to represent substrate again, in this example we will need to imagine more than one bed. 100 beds are an easy number to use when thinking about percent, so let's start with 100 beds in 100 rooms. At a low substrate concentration such as 1 cat per room, we probably wouldn't see many cats in the beds when we checked. But by increasing the number of cats in each room, the bed occupancy would also increase. Eventually, when we checked, we would see half of the beds occupied. At this point we have a number that represents the affinity of the cats for the beds, or substrate affinity of the enzyme for its substrate. This is the number of cats we need to add to the rooms to guarantee half of the beds are filled. This represents the halfway mark between never finding a cat in a bed and the upper limit where we would never see an empty bed. As we can see with our mass action term in the equation, solving for the percent bound, when the concentration of substrate equals the affinity constant, gives us a value of 1/2 or 50%. All binding curves work on this relationship, and the only real difference between the Michaelis-Menten equation and other binding curves is the addition of the term defining the enzyme's catalytic rate. known as the maximum reaction rate, or Vmax, which is a reflection of the catalytic rate of each enzyme multiplied by the total enzyme population. Now that we have the basis for understanding the Michaelis-Menten equation, we can see that the competitive and non-competitive inhibition equations are produced by the addition of the same inhibition term to the Michaelis-Menten equation, making them look very similar. But this term affects the Michaelis-Menten equation in completely different ways according to the inhibition equations. In competitive inhibition, we're multiplying the substrate affinity by the inhibition term, whereas non-competitive inhibition involves dividing the maximum velocity by the inhibition term. Although puzzling, this inversion is the reason for the reduction in activity associated with non-competitive inhibition and the linear increase in substrate affinity associated with competitive inhibition. In addition to the unusual inverse effect the inhibition term has in these equations, it also looks odd because contrary to all other molecular interactions, it is not defined using a binding curve. But this is just an illusion, as upon rearrangement, it turns out to be the inversion of a binding curve defining the fraction of the enzyme population not bound by the inhibitor. This explains why the non-competitive equation works so well, as when we divide the reaction rate by the inverted binding curve, the reaction rate is now defined by the portion of the enzyme population free of inhibition. Or using our previous analogy shows that cats can only occupy beds that aren't blocked by dogs. But what does multiplying the substrate affinity by an inverted binding curve mean for competitive inhibition? Historically, the inversion of the Michaelis-Menten equation has been used to determine the equation's parameters, as this inversion linearizes the data, resulting in an easier way of determining the constants of the binding curve. As a straight line, the substrate affinity and reaction rate constant can easily be determined by the intercept points of the line on the x and y axis. It's a neat trick that simplifies the analysis of enzyme kinetics and suggests why the competitive inhibition equation, with its inverted mass action term for inhibitor binding, produces a linear change in substrate affinity. That being, the substrate affinity is being multiplied by the equation of a straight line, which results from the inversion of the inhibitor binding term. So, there is a mathematical explanation for linear change in substrate affinity required by the competitive inhibition equation. However, this mathematical explanation for the linear change does not explain how the percent of the uninhibited enzyme population would influence the interactions between substrate and individual enzymes. This interaction is implied by multiplying the substrate affinity with the inhibition term, as this results in the substrate affinity being divided by the fraction of the uninhibited enzyme population. This highlights one of the major failings of both the competitive and non-competitive inhibition equations, which is their inability to distinguish between a mass action effect, which relates to the binding of inhibitors to the enzyme population, and the effect an inhibitor has on an individual enzyme. In non-competitive inhibition, this simply means once an inhibitor binds the enzyme is no longer functional. While in competitive inhibition, the linear change in substrate affinity relies on the bizarre concept that an individual enzyme's interaction with its substrate is influenced by the fraction of the enzyme population not bound by the inhibitor. This is counterintuitive and does not align with the notion that inhibition results from a direct interaction between the inhibitor and the enzyme. So it's not surprising that competitive inhibition has never been observed experimentally. So is there a better way to model inhibition? The idea of competitive inhibition is obviously fine. An inhibitor can block the active site of an enzyme by mimicking the substrate. But the competitive inhibition equation does not model changes in substrate affinity in any useful way. Instead of overcomplicating things, changes in substrate affinity can be modeled using an ordinary mass action binding curve where the endpoint is not infinity, but a new value defining the effect the inhibitor has on the substrate affinity. The induced change could be positive or negative, and you could think about this again using our cat analogy, where an increase in substrate affinity might be represented by having the bed in a sunny spot increasing the likelihood of a cat napping there. Or, the change could be negative, as we saw when the dog is placed next to the bed. This simplification allows us to understand changes in substrate affinity as a shift between two enzyme forms, one with and one without an inhibitor. This also solves the issue of the lack of distinction between the mass action binding portion of the equation and the quantification of the effect an inhibitor has on the substrate affinity of an enzyme. As such, this approach can also be used with the non-competitive equation. By introducing a new term defining the effect the inhibitor has on the enzyme, the inhibitor-induced catalytic rate can now be something other than zero. And we have a new equation that can define full inhibition, partial inhibition, or even activation of the enzyme's activity. Now we can combine our new equations describing changes in substrate affinity and changes in enzyme activity to produce a single equation for describing almost any effect you can imagine an inhibitor or activator may have. This is only possible by recognizing the problem with the traditional inhibition term. And the resulting equation replaces a large number of equations that have been used to describe perceived different forms of inhibition and activation, with a great deal of them incorporating the classical inhibition term without recognizing what it is. Now you might be wondering, why does this matter? Well, it's crucial because these inaccuracies in the foundation of inhibition theory have led to a century of complex equation derivations attempting to improve our modeling of enzymatic systems, but ultimately reincorporating the same inverted mass action terms into these models. These complex models have caused confusion and decreased research in these fields, encouraging the dominance and use of IC50 values and the original inhibition equations. This has impacted our understanding of biological interactions and our ability to develop drugs based on more complex mechanisms of action. It's time to rethink how we understand and teach these concepts, ensuring that we're building on a strong, reliable foundation. So, where does this leave us and how has it impacted the world of biological research? Join me on this channel as we explore these questions, dig into the nuances of biochemistry, and uncover the exciting developments and challenges in our field. If you feel like getting in touch, I am available for consulting or tutoring, and if you are interested in enzyme kinetics and drug modeling, I am planning to put out a course on the topic soon. Thanks for tuning in, and if you enjoyed this video, be sure to like, subscribe, and ring the bell for more thought-provoking content.